In this video, we continue our discussion of polarity by taking a look at reviewing molecule polarity. So molecules, like bonds, can be described as being polar or nonpolar based on electron distribution. Molecule polarity depends on the presence of polar versus nonpolar bonds and the molecular shape. So to be a polar molecule, this results in the uneven distribution of electrons. Electrons get pulled towards one end of the molecule. So remember when we talked about bonds, the electrons were pulled towards one end of the bond. Here they're pulled towards one end of the molecule. For this to happen, this requires polar bonds to be present, and in particular, it requires an unsymmetrical geometry. So when we talk about an unsymmetrical geometry, what we're doing is we are looking at our center atom, and we're looking to see what's around it. If at least one corner of the geometry is different from the others, then it is unsymmetrical geometry. With a nonpolar molecule, we have an even distribution of electrons. This occurs when our molecule contains all nonpolar bonds. So if the bonds aren't pulling electrons, then they're not being pulled towards one end of the molecule. The other possibility is that we have a molecule with polar bonds, but they're in a symmetrical geometry. When we talk about a symmetrical geometry, that occurs when all corners are identical. So we're going to look at some molecule examples. First, we're asked to draw the dot structure for ammonia. If you need a review for drawing dot structures, there are videos and PowerPoints in your additional resources folder in Blackboard. But if we were to draw the dot structure for ammonia, we would have our nitrogen in the center. We would have single bonds to each of our three hydrogens. And then to use up all of our electrons and fill nitrogen's octet, we have a lone pair on the nitrogen. So using this dot structure, we are asked to use dipole arrows and partial charges to indicate any polarity. So we're looking at our individual bonds. If we look at our nitrogen-hydrogen bonds, those are bonds between different atoms, so that's going to be a polar bond. The nitrogen is further to the right in the periodic table, making the nitrogen more electronegative than my hydrogen. So that means my nitrogen would be partially negative and my hydrogen would be partially positive. So my dipole arrow starts on the hydrogen and it points towards my nitrogen. Now we need to look at all bonds. So each nitrogen-hydrogen bond is polar. So each hydrogen is partially positive. So along each of my bonds, I have this dipole arrow pointing towards my nitrogen. Now next we're asked about the molecule geometry. So we got to go back to our valence shell electron pair repulsion theory back from first semester chemistry. If we look at this structure, we look at our center atom. I've got electron pair, electron pair, electron pair, electron pair. So that gives me a coordination number or electron cloud number equal to 4. So if I have 4 groups of electrons, those form a tetrahedral geometry, but that's the electron geometry. We're being asked about the molecular geometry, which is the arrangement of the atoms. So that depends on whether or not we've got lone pairs or bonding pairs. I have 1 lone pair and I have 3 bonding pairs. That corresponds to our trigonal pyramidal geometry. Notice when I drew my dot structure, I drew it in that trigonal pyramidal geometry with the electron pair on top and my hydrogens at the base of my pyramid. Now next we're asked if the molecule is polar or nonpolar. Now before we get there, the other thing we want to take a look at is it symmetrical or unsymmetrical? So when we're looking at that symmetry, I have my hydrogen, hydrogen, hydrogen at the base. So the base is all the same, but the top of my tetrahedron here is different. I have one corner different from the others. So that's going to make this molecule unsymmetrical. So when we look at polarity, we can look at two things. We can look at our dipole arrows, and we could see whether or not our dipole arrows are creating a net dipole. So to have a net dipole, our arrows have got to be pointing in a general direction. If we look, all of our arrows are pointing to the top of that nitrogen. So that gives me a net dipole. So based on that, I could judge that this is polar. The other possibility, without having to draw any of these partial charges or the dipole arrows, I could simply look at my symmetry. I have polar bonds, and I've just identified my geometry as being unsymmetrical. So if I've got polar bonds in an unsymmetrical geometry, that's going to make my molecule polar. Now next we're asked to take a look at water. So if we draw the dot structure of water, I've got oxygen in the center, single bonds to my two hydrogens, and then two lone pairs of electrons. I have oxygen-hydrogen bonds. These bonds are polar. They're bonds between different atoms. The oxygen is more electronegative because it's further to the right in the periodic table than hydrogen is. So the hydrogen is going to be partially positive. My dipole arrows start on my hydrogen and they point towards my oxygen. Now when we look at geometry, again, I count my electron groups. I've got 4. So I have a coordination number or a charge cloud number of 4. It consists of 2 lone pairs and 2 bonding groups. When I have that combination, remember that gives us a bent molecular geometry. And so I've represented that geometry in my dot structure. I have drawn it in that bent format. If we look at symmetry, so we're looking at our center atom and what's at the corners. So I have lone pair, hydrogen, hydrogen. My corners are different. If my corners are different, it's unsymmetrical. So in determining molecule polarity, again, we can look at our net dipole. We see that the electrons are all being pulled up towards the oxygen. So my electrons are all concentrated up there with the oxygen. They're being pulled away from the hydrogens. So that's going to make it polar. Or again, we could look at our symmetry. I've got polar bonds with unsymmetrical geometry. So that combination is going to give me a polar molecule. So now we've just taken a look at ammonia, NH3, and water. And we're asked in problem 10, which molecule is more polar? So I've got my NH3, which we said was polar. And then I've got my water, which we said was polar. And we're asked to identify which one is more polar. So they're both polar molecules. When we're looking to see who is more polar, we actually look at two things. We're going to look at electronegativity differences and the number of polar bonds. So when we look at the differences in electronegativity, the greater the difference, the more polar the bond, the more polar the molecule. So here, if we compare nitrogen and oxygen, oxygen has the greater electronegativity, which means that the oxygen-hydrogen bonds are more polar than the nitrogen-hydrogen bonds, which means that the water molecule will be more polar than the ammonia molecule. Now, we also mentioned number of polar bonds. So to be a polar molecule, my electrons have to be pulled towards one end of the molecule. What we're going to find is that as the number of polar bonds increases, the overall molecule polarity decreases. That's because as we get more polar bonds, the greater number, the electrons actually spread out. And as the electrons spread out, they become less polar. And so we'll see this in another example. Now next we're asked to draw the dot structure for carbon dioxide. So for that dot structure, we would have carbon in the center with double bonds to oxygen on each side. We end up with this linear geometry. Now we're told that this is a nonpolar molecule. So we're asked to explain. Now if we look at this, the carbon-oxygen bonds are polar. The oxygen's more electronegative. So I have dipoles on each side. The issue is, if we look at these, it's the same atom on each side. So these dipoles are the same. And they're pulling in opposite directions. The consequence of that is that my electrons get pulled onto both sides of that molecule equally because the atoms on either side of the center are the same. They're pulling the same. We can see that these dipoles cancel one another, giving us a nonpolar molecule. We could also look at this in terms of symmetry. My center atom, it's linear, so there's only two sides. One side's oxygen, the other side's oxygen. Both sides of that geometry are the same. So if it's symmetrical, the electrons get pulled across all sides of the molecule, it becomes nonpolar. So the final thing we want to take a look at with this worksheet is problem number 12, determining if the following molecules are polar or nonpolar, and we're asked to rank them in order of increasing polarity. So as we start out doing this, we want to start by drawing our dot structures. Now, hopefully, the more practice you get, you should be able to do this without your dot structures. But if we go ahead and draw our dot structures, I have my CH3F, I have my CH2F2, I have my CHF3, and then finally I have my CF4. So I've got my dot structures drawn. If I look at my bond types, in all of these molecules, I have carbon-hydrogen bonds, which are nonpolar. And then I have carbon-fluorine bonds, which are polar. So the carbon-fluorine bonds are going to have my partial negatives. So I'm going to have a dipole here on my CH3F. My CH2F2, I've got two fluorines that are both partially negative. And then same thing with my remaining molecules. So all of these molecules have got polar bonds present in them. Because they're all dealing with fluorines, we're not looking at electronegativity differences because they're all the same bond polarities. So what we've got to look at are the number of polar bonds. So we said before that as the number of polar bonds increases, the overall molecule polarity decreases. So my molecule with the one polar bond, and that's going to be a polar molecule because it's a polar bond, it's got one corner different than the others, and it has only one polar bond. My CH2F2, again, it's unsymmetrical. I've got two fluorines and then two hydrogens. Since it's unsymmetrical with polar bonds, it's polar. My CHF3 is polar. Again, I've got three corners are fluorines, but one is hydrogen. One corner is different, it's unsymmetrical. And then I've got my CF4. All corners are the same. It's symmetrical, so it is non-polar. So now when we go to rank these, my CF4 is going to be the least polar. Because even though it has those polar bonds, they're all fluorines. And so each fluorine is pulling the electrons the same. So the electrons are getting pulled the same towards every single corner of that tetrahedron, which results in the electrons being evenly distributed. And so if they're evenly distributed, the molecule as a whole is nonpolar. Now, my molecule with one polar bond has my electrons being pulled very strongly towards that one fluorine. So we have this strong pull towards one corner. As we have more polar bonds, the electrons kind of spread out across the molecule. Now they're spreading out across two corners of my tetrahedron. Here it's being spread out across three corners. And so as they spread out more, it becomes less polar. So my CF3H is my next in polarity, my CH2F2, and then my CH3F will be my most polar. Now, if we were to judge this without drawing our dot structures, we see those fluorines present. So we know the carbon-fluorine bonds are going to be polar. So we can tell right away, just by looking at that, because of that fluorine being present, we've got polar bonds. If we have a CF4, carbon forms four bonds, they're all the fluorine, that's automatically symmetrical and nonpolar. So that leaves us with ranking our remaining three. So the more fluorines I have, the greater number of polar bonds I have, the less polar the molecule becomes. So this review of polarity between bond polarity and molecule polarity, again, this is foundational for this course. We're going to have to use that distinction between ionic and covalent all semester long. Polar and nonpolar all semester long. We can't do or determine things like our properties or calculations in later chapters if we can't do these basics of polar versus nonpolar.